does your wage go up as you get older? If so, how much? How would you measure that? In this video, we're going to learn about linear regression, simple linear regression, where we could measure things like that. So let's say, first of all, that we plotted on an XY axis people's age and their hourly wage. So you basically ask a bunch of people, how old are you? What's your hourly wage? And any given person becomes a data point. So let's say these are data points over here that you have. And again, different people have very different values. You might have somebody here who's 70 years old and only makes 10 bucks an hour. They're over here. You might have somebody here who's 20 and makes $80 an hour. They're over here. But for the most part, the trend looks something like this. Now, in pure mathematics, you get 2 points and bam, you could make a line, an mx plus b, that passes exactly through those 2 points, and life is beautiful. But in the real world of messy statistics, you have like 1,000 points over here, and there's not going to be a single line that passes through all 1,000 of them. And that is the art of regression. We're trying to find a line that passes, as closely as possible through these points. So overall, first of all, looking at this, let's define this thing called a residual. So here's what that is. Looking at this, let's say you are a 23-year-old. According to this graph, let's say if you were to look at this red line, let's say the red line predicts that you make $18 per hour. But let's say in reality, your actual data point over here is at 21. So let's say you really make 21 an hour, but this line, this line that is hypothetically the line of best fit, says that you make 18. So this $3 gap, the fact that, again, not every point is on the line, they're a little bit off, that gap is called the residual. So the usual notation for that is U. So U is the residual, and really what it is it's just the gap between the point and the line. And so clearly every person here has a residual. Some are positive, some are negative. If you're above the line, then you have a positive residual. If you're below the line, you have a negative residual. And here's where we're going to use summation notation. The sum of all the residuals is 0. So all of the residuals add up to 0. That kind of makes sense because, those on average who make more than predicted and those who make less than predicted sort of cancel out if we truly have that line of best fit, that mx plus b that truly does go through, the middle of those. But again, we don't even know how do we find that mx plus b, that best mx plus b. So that best mx plus b has 2 characteristics. One is that it's going to be one where the residuals do add up to 0. So on average, it's passing through all the points. But the other is this, is that we want to minimize the sum of the residuals squared. So what does all that mean? Well, the residuals could be positive or negative, as we said, but really what we're interested in is the distance. How far off is the residual, is that data point, from the line? How far off that distance is. Now, when you square something, whether it's negative or positive, it now becomes positive, and it kind of can help represent that distance, right? Rather than the negatives and the positives canceling each other out, by making them all positive first and then adding them all up, that's giving us a sense of how well does this line do at capturing those points. What's sort of that distance? And so the bigger the sum of the residuals square, the further off the points are from the line. And so that's why we want to minimize the sum of the residuals squared. And that's why that process is called OLS, ordinary least squares, your least squares, right? So you're minimizing the square of the residuals. So that's that whole process And again, I'm not even going to do the calculus involved because programs like R can do them in a heartbeat. Essentially what you do is you feed it all those data points, and in a heartbeat, it'll tell you what the slope and intercept would be of this line, what that y equals mx plus b, what that optimal slope and intercept are. And again, in statistics notation, instead of mx plus b, let's get used to calling that b0 plus b1x. And here, for our purposes, when we do that, when we have those data points and we run a regression, we're going to focus on what the computer says our b1 is, our slope. Because that slope here, let's say that slope you get is 2. What that means is, on average, as your age goes up by 1, on average, the wage goes up by 2. That's what that would mean if that's what the data say over there. Now, the question then is, well, is it really 2? Or is it 2.1? Is it 0? Who knows? So usually when you do a t-test, you can test whether that slope, whether you can rule out certain numbers. And so if somebody's claiming that, no, on average wage doesn't go up at all as your age goes up, they're making the claim that the slope is truly 0. And so what you could do is you could do a little t-test, which is just a way to test whether the slope is equal to a particular number or not. And so if the slope that you got in your data was 2, you could do it. The t-test is saying, is that slope equal to 0 or not? Like, can we confidently reject 0 as the true slope if 2 is what we found in our sample? Because keep in mind that this regression is still just for our sample. If we were to truly get everyone in the population, the slope might be a little different. So that's really what this is we're trying to rule out whether the slope is truly 0 or not. Now, in this whole regression process, there are a couple of assumptions that we make. A lot of them are just, technical math things, but I'm going to focus on 2 of them just to talk through a little bit. One is that there is no heteroscedasticity. So what is heteroscedasticity? One interesting thing to do with regression is to actually kind of plot out the residuals themselves. So here, in a perfect world, something like this, if we were to look at the residuals, if instead of the line being like whatever angle it is, if we were to put that line sort of like this, the residuals around that line sort of might look something like this. So if the residuals look like this, then you're good. But what if the residuals look like this, where, how much they vary, how much the residuals are going above and below the line, that's not the same everywhere. It's like, all right, the residuals are kind of close to the line here, but far from the line here. Again, what this might look like in your actual mx plus p is something like this, where if this is your line, maybe your data points look like they're close to the line here, but then they're further here, and then they're even further there. So whenever the variance changes as you go to different x values, that's called heteroscedasticity. Hetero meaning not the same. It's a different variance here versus here. So whenever you have heteroscedasticity, your inference is going to be a little bit off. And so there is a way in regression to correct for that. And so, that's called using robust standard errors. So whenever you're doing regression, if you do robust standard errors, that's a way to correct whether or not there's heteroscedasticity in your data. Finally, the other thing to check for when you're looking at your regression is whether there's any patterns in the residuals. So let's say your residuals, the pattern looked something like this, where all the residuals are negative, then all the residuals are positive, and then all the residuals are negative again. Whenever your residuals have a pattern, that might be a sign that your true relationship is nonlinear. So what if your data points actually looked like this? If your data points kind of looked like this, you can still do a regression. You could still plot an mx plus b through those data points, but then what you're going to see is your residuals aren't uniformly distributed. It's kind of like they're all negative here, then they're all positive here, and they're all negative here again. So whenever that's the case, notice that instead of this blue line, what's better is this blue nonlinear function, right? So whenever there's a pattern in your residuals, that might be a sign that you should try to do something nonlinear instead of a linear regression.